Welcome back, everyone. Indonesia is rapidly expanding its use of geothermal energy, aiming to become one of the world's top producers of this reliable and renewable power source. Located along the volcanic ring of fire, the country has access to some of the richest geothermal reservoirs on Earth. Until recently, much of this potential remained untapped due to infrastructure challenges, financing limitations, and regulatory complexity. Now, with increased government support and international investment, new geothermal projects are moving forward at a record pace. Indonesian engineers and energy planners are focusing on both large utility-scale plants and modular systems suited for rural deployment. This approach allows the country to meet rising electricity demands while reducing dependence on imported fossil fuels. The acceleration of geothermal development marks a significant milestone in Indonesia's broader energy transformation strategy and positions the nation as a leader in clean power generation across the Asia-Pacific region. Indonesia's geothermal systems begin with the identification of underground heat sources located in volcanic regions. These regions are mapped using geological surveys, satellite imaging, and seismic activity tracking. Engineers drill exploratory wells to determine the temperature, depth, and pressure of the underground reservoirs. If a site proves viable, production wells are drilled into the heat zones. Water or naturally occurring steam is then drawn up from these wells and used to drive turbines. Accurate mapping is essential to avoid dry wells and to ensure consistent output. Multiple wells are typically arranged in clusters to provide reliable flow and redundancy in case of maintenance or failure. The heat extracted from underground reservoirs can exist as either dry steam or hot water. In a dry steam system, the steam is sent directly to turbines that convert thermal energy into mechanical motion. In a hot water system, the water must first be separated into steam and brine using flash separators. The flash process involves reducing pressure on the hot water so that part of it rapidly vaporizes. The resulting steam drives the turbines, while the remaining brine is cooled and re-injected back into the reservoir. This closed-loop method helps maintain reservoir pressure and prevents environmental discharge. Binary cycle plants are another common design used in Indonesian geothermal projects. These systems are ideal for medium-temperature resources that cannot generate steam directly. Instead, geothermal fluid is passed through a heat exchanger, where it transfers its heat to a secondary working fluid with a lower boiling point, such as isobutane. This fluid vaporizes and turns a turbine, then condenses and returns to the exchanger. The geothermal water never comes into contact with the turbine. This design enables efficient use of heat sources that would otherwise be considered too weak, expanding the number of viable geothermal locations in Indonesia. The turbines used in geothermal plants are specially engineered to operate under continuous heat and moisture conditions. Steam turbines must be able to handle rapid pressure changes, mineral content in the steam, and corrosive gases such as hydrogen sulfide. The blades are made of high-strength stainless alloys, and the turbine casing is fitted with seals and insulation to minimize energy loss. Control systems monitor temperature, pressure, and rotational speed, allowing for adjustments in real time. Turbine efficiency is critical to overall plant output, so regular maintenance and performance tracking are conducted to prevent declines in efficiency over time. To convert mechanical energy from the turbine into electricity, geothermal plants use synchronous generators. These machines are connected to the turbine shaft and rotate at precise speeds to maintain consistent frequency output. Voltage regulators and transformers condition the electricity to match the local or national grid requirements. The generators must also be protected from heat, moisture, and vibration. Cooling systems, both air-based and water-based, are used to keep the generator within safe operating temperatures. Real-time monitoring ensures that output remains stable and backup systems are in place in case of any fluctuation that could damage connected infrastructure. The cooled geothermal fluid and residual brine from the process are typically re-injected into the same underground reservoir through separate wells. This is a critical environmental and operational step that helps sustain the resource. Without re-injection, the reservoir could experience pressure loss or depletion over time. Injection wells are designed to minimize thermal shock and clogging. Engineers monitor the temperature and chemical balance of the re-injected fluid to avoid damaging the surrounding rock or causing mineral scaling. Properly managed re-injection ensures the sustainability of the geothermal field and helps mitigate induced seismic activity. Remote control and automation technologies play an increasingly central role in Indonesian geothermal plants. These systems use sensors and programmable logic controllers to monitor every stage of energy production. Data from flow rates, temperature sensors, and pressure gauges are sent to centralized control rooms, where operators can adjust parameters without being on site. This remote capability reduces the need for manual labor, increases safety, and allows for much faster responses to anomalies. Predictive maintenance algorithms can even anticipate equipment failures before they occur. These technologies help improve uptime and reduce operational costs across geographically dispersed geothermal facilities. Geothermal sites in Indonesia often face challenging terrain and seismic risks. To handle these conditions, engineers design flexible infrastructure that can adapt to ground movement and thermal expansion. Pipelines are built with expansion joints and insulation to manage fluctuating temperatures. Foundations for heavy equipment are reinforced to prevent settling or vibration damage. Monitoring stations track seismic activity and structural integrity, allowing rapid shutdown if needed. These protective measures are essential in a country with high volcanic and earthquake activity. Building resilient infrastructure ensures long-term reliability of energy delivery and minimizes the risk of costly disruptions. Transmission infrastructure connects geothermal power plants to residential, commercial, and industrial consumers. Because many geothermal sites are located in remote or mountainous regions, high-voltage transmission lines are required to minimize loss over long distances. Step-up transformers raise the voltage for efficient travel across transmission lines, and step-down transformers reduce it for local use. Substations monitor the flow of electricity, isolate faults, and balance the load between different parts of the grid. Indonesia is investing in modernizing its transmission system to support integration of more geothermal plants. These upgrades improve reliability and prepare the network for future increases in clean energy output. In the future, Indonesia may develop fully modular geothermal systems that can be rapidly deployed in remote or island regions without access to large power grids. These systems would include compact drilling rigs, self-contained binary cycle plants, and automated control modules housed in prefabricated units. They could be transported by truck, ship, or helicopter and installed within weeks instead of years. Once operational, these systems could power rural clinics, schools, or small industries using only local geothermal heat. Combined with smart grid coordination and battery storage, such modular units could help Indonesia electrify its outer provinces while reducing dependency on overseas energy sources and centralized infrastructure. If this momentum continues, Indonesia may not only meet its domestic energy goals, but also export geothermal expertise and technology across the region. Future geothermal projects could include hybrid systems that combine geothermal with solar or biomass, increasing efficiency and reliability for off-grid communities. Advanced digital control systems are being considered to optimize thermal output and reduce operational costs. As the network of geothermal facilities grows, Indonesia could use this steady baseload power to support battery manufacturing, electric mobility, and industrial development in areas previously underserved by the grid. With its geological advantage now matched by political will and technical capability, Indonesia is turning a natural resource into a foundation for long-term economic growth. Thank you very much for watching. Please like and subscribe.